Alright, so today we're going to be starting chapter 34, which is geometric optics, so lenses, mirrors, cameras, telescopes, stuff like that. We're going to see how they work. And it's geometric optics because, as you're going to see, we're going to be using a lot of geometry to solve some of the equations that we have. So I personally think that the geometric optics chapter is the hardest just because there's a lot of vocabulary to learn. And a lot of just like sign rules and stuff that aren't necessarily that intuitive. So I personally think this is at least the most memorization intensive chapter that we're going to do. So we'll see what you guys think as we get through it. So, okay, so the first thing we're going to do is just define some of our words. So we're going to be talking about images and objects when we talk about optics. So as everybody's seen when you look in the mirror, so let's say that's our mirror. You are the object here, and you see an image of yourself in the mirror, like what looks like to be behind the mirror. So that's what we mean when we say image and object. Object is just the thing that, like, the actual physical object that's being either reflected or refracted, and then the image is formed by those light rays, which we'll see obviously in more detail soon. So by an object, we mean anything from which light rays radiate. So that could be something like a light bulb that is self-luminous, as we say, it emits its own light. So like a light bulb, the sun, those are all self-luminous. But as we'll see in a second, even objects that aren't self-luminous, we're still going to draw the light rays as coming from them. Kind of like how even though the moon isn't self-luminous, it still lights up, it still has light coming from it because it's reflecting the light from the sun. And then when we talk about a point object, that's obviously an object that's a single point, so it's zero-dimensional, just a single point, no height, no width, anything like that. So we'll be looking at point objects, and then we'll also be looking at extended objects, which obviously have some kind of physical extension, so they'll have height, width, depth. Any physical object that we look at is going to be an extended object, obviously, because we can't, we don't have just single zero-dimensional points that we can look at in the real world. So as I was saying before, an object always has, when we draw diagrams for geometric optics, the object always is drawn with the light rays coming from it. So even if this object here is not self-luminous, we still draw the light rays as coming from that object. And again, it's similar to how the moon reflects the sunlight. It looks like the moon is giving off its own light, even though we know it's really not. So it's the same idea. So all of our objects are going to be drawn with light rays emanating from them. We're not going to worry about the fact that they're really being reflected from like a light bulb, on the ceiling or something like that. So we're just looking at the light rays coming from the object itself. So if we look at the case of a plane mirror, so that's just the kind of mirror that everyone has in their home, just a straight, flat mirror. So if we put an object in front of a plane mirror here, we have light rays coming from it. They will hit the mirror and then be reflected back according to the law of reflection. So the incident angle is the same as the reflected angle, as we know. So all of these light rays will hit the mirror and then be reflected back with the same angle of incidence. So and this is called the object, and we call the point P where the object is the object point. And then if you notice, if you draw back all of these reflected rays, so these are all the reflected rays here, if you draw them back and just extend them back into the mirror, you'll see that they all converge on a point here. So we call that P prime, that's the image point. And that means that it looks like, when you look in the mirror, it looks like these reflected rays are emanating from the image point, right? When you look at yourself in the mirror, it looks like those light rays are emanating from the you behind the mirror, right? So that's the image point, and that's what we call the apparent source of the reflected rays. And that's denoted P prime, as we said. And then we have what's called real and virtual images. So a virtual image is what we just had. A virtual image just means that the light rays do not actually pass through the image point. It just looks like they emanate from it. So as you can see here, on the other side of a mirror, there's obviously really no light rays behind the mirror, right? Because it's just like your bathroom wall or something. So there's no actual light rays where it looks like the image is, right? The image point has no actual light rays coming from it. They just look like it. So this is what's called a virtual image because there's no light rays actually passing through it. then we can have what's called a real image, where light rays actually do pass through the image point. We're going to see that as we go on to different types of reflection. So we're going to see examples of a real image later where the outgoing rays really do pass through the image point. Okay, so let's look a little more at plane mirrors. So we have here point P, the object, and point P prime, the image. And then we denote the distance from like the surface of the mirror as S for the object distance and S prime for the image distance. So since this is geometric optics, you can use geometry to show that S and S prime have to be the same magnitude. So you can make your triangle here. So you've got this flat mirror surface. You have the object distance S. You have some random light ray here that has an angle of incidence theta. It bounces off with the angle of reflection theta. And you can show that this triangle and this triangle are congruent, so they're the same exact size. You can show that S and S prime have to be the same magnitude. Now I said that they're only the same magnitude because we do have a sign convention for the image distance and object distance. So for the object, so over here, the object, we say that the object distance is positive if it's on the same side as the incoming light. So in the case of like a mirror, when you're looking at yourself in the mirror, you are obviously on the same side of the mirror as the light, right? Because wherever your light is, you're on the same side of the mirror as that. You can't see yourself in a mirror if the light is on the other side of the mirror. So for the case of a plane mirror, the object distance is always positive because the incoming light is on the same side of the mirror as the object. Now, for the image distance is not positive. The image distance, we use the outgoing light to denote the positive or negative. So the positive side is where the outgoing light is. So in the case of a mirror, the outgoing light, since it just gets reflected off the surface of the mirror, the outgoing light is on the same side as the incoming light. So since the image is on the opposite side of the mirror as the outgoing light, it's a negative. So the image distance is actually negative in the case of a plane mirror, and the object distance is positive. Now we're going to see some cases where the image distance is positive when we do refraction, but for a mirror, the image distance is negative because it's on the opposite side of the mirror as the outgoing light. So then I just rewrote that here. So for a plane mirror, the image and object distances are just related by this equation here. So they're obviously the same magnitude, but different signs. So S is positive, the object is always positive, the image distance is negative. And these are both measured from the surface of the mirror, obviously. Okay, so now we're going to talk about extended objects in a mirror. So before we were just looking at point objects. Now when we have a extended object, it can be magnified, right? Everyone's seen kind of in those funhouse mirrors where you can get like stretched or shrunk if the mirror is curved. So that's called the magnification. And now with a plane mirror, we all know that the magnification is just the same, right? You don't look a different size when you look in the mirror if it's just a straight flat mirror. So you can again use geometry to show that this is the case by showing that this triangle and this triangle are the same. So here we call the object height y. So y denotes the object height, so it's just this height here, this distance. And then the image height we call y prime, so that's right here. So you can just show that this side of the triangle and this side of the triangle are the same size, so the image and object have the same height. And now that means that the magnification is 1 because they have the same height. There's nothing, it's not bigger, it's not smaller, so there's no magnification going on. So for the case of a plane mirror again, we say that the lateral magnification, how much it is stretched or shrunk, is just 1. And the lateral magnification is always given by y prime over y. So that's the image height over the object height. And as we said in the case of a plane mirror, these are the same, so the magnification is just 1. Now, one thing that you might see in some homework problems is when you have multiple mirrors, and well, what's the image, what's the object when you have multiple mirrors? So the image in one mirror can actually serve as the object for another mirror. So here let's say we have some object at point P here. Now these rays then go to this first mirror here, right? And then they're reflected off this mirror, and now they go to mirror 2. But mirror 2 thinks that the object is actually back here. So the object for mirror 2 here is really the image in mirror 1. Because if you trace these rays back, it looks like there's an object here at P prime, even though it's just an image. So then these rays go here, and then now these rays, so when they're bounced off mirror 2, if you extend them back, it looks like there's another image here, P3, and that's the final one that you end up seeing when those light rays bounce off mirror 1 and then mirror 2. So that's just something to keep in mind. Sometimes you might have multiple mirrors or multiple lenses when we do lenses on Thursday, and the image of one might serve as the object for another, so that's just something to keep in mind. We're not going to do any explicit examples with that today, but we definitely will on Thursday. Okay, so one thing to keep in mind with mirrors, which I'm sure everyone has had experience with already, is that they change the handedness, what's called the handedness of your system. So if you have a right-handed system, we do a right-hand rule, we have a right-handed system on our side of the mirror. In the mirror, it looks like it's actually the left hand, right? Everyone knows that if you your right hand in a mirror, it looks like your left hand. So mirrors reverse the handedness of a system. So here we have what looks like a left-handed coordinate system over here, and in the mirror, the image, it looks like actually the right-handed coordinate system. Now, since I'm a theorist, we'll go on a little tangent about left and right-handed systems in particle physics. So in particle physics, we have what's called left-handed and right-handed particles. Now, obviously, we're not going to get into what makes a particle left-handed and right-handed. You can just think about your hands. So we have every particle has a left-handed and a right-handed version. And now the weak force, which is what governs nuclear decays, so like beta decay, any kind of radioactive decay, that's the weak force. The Higgs boson is also very closely related to the weak force. It kind of like governs the weak force. And that's what I study actually, is the weak force. So for some reason, the weak force only interacts with left-handed particles, and we don't know why. That's one of the big unanswered questions in physics, is why does the weak force, why does the Higgs boson, why does the W boson, the Z boson, why do they only interact with left-handed particles and not right-handed particles? If you take an electron, you have a left-handed electron and a right-handed electron essentially. And for some reason, the weak force only sees left-handed particles. All neutrinos, whenever you have a nuclear decay, there's always a lot of neutrinos released. All neutrinos are left-handed. We don't know why there are no right-handed neutrinos, but there are only left-handed neutrinos, and we don't know why. So that's a big question that's still unanswered in physics. So this was actually theorized that the weak force might not basically obey mirror symmetries. So the woman that actually did the experiment to prove this was called Chen-Xiang Wu. So that's her here with her experiment. So she actually did an experiment using cobalt atoms to show that if we have a, this is essentially, she used a big magnetic field and cobalt atoms, and showed that if we do this experiment, in the real world here, that the mirror image doesn't happen. So if you just, took this experiment and its results here with the electrons flying out, and reversed it to a mirror, the mirror image doesn't happen. So the mirror image of this physically doesn't happen, which is very weird when you think about it, because there's really nothing in our day-to-day life that, if you want to pick something up with your right hand, you can just as easily pick it up with your left hand and it looks the same. So this is a very weird and interesting property of the weak force, that it only sees left-handed particles. And I linked an article here if anyone's interested in that. But okay, so that's enough of a tangent for that. So let's go on to talk about spherical mirrors. So we need a little bit of vocabulary to talk about spherical mirrors first. So when we talk about a spherical mirror, that's kind of just like any mirror that's a little bit curved. So even like a spoon, you can kind of think of as like a spherical mirror. So a spherical mirror will have a radius of curvature. So that means if we have the mirror here like that, if you sort of traced it out and made the whole circle with it, we have the radius of curvature here. So the radius of curvature is just like, what would the radius of that circle be if you traced out, a full circle from the mirror. And the center of curvature is just obviously the center of that circle. So the center of curvature is just this point right here. The vertex, which we denote V, is the center of the mirror surface. So if this right here is just the piece of mirror that we have, the vertex is just the center of that. And then we call this line from the center to the vertex the optic axis. So you just draw a line from the center here. It's going to obviously be one radius in length, and then that's the optic axis. Okay, and then just one more thing. So then we obviously have concave and convex. So that's like the number one thing that everyone confuses is convex and concave lenses. So a concave lens will look like this. So this is concave, and then this would be convex. And now obviously it matters what side the light is coming in on. So in both of these, I have light coming in from the left, right? Because obviously if I had light coming in from the other side, it would switch which one's convex and which one's concave. So if the light's coming in here and the mirror sort of makes like a little cave, that's concave. And then if the light is coming in over here and the mirror sort of bulges out, that's convex. So we're going to be looking at concave lenses first. And then let's just do, there's also some sign conventions for convex and concave lenses. So for a concave lens, we know the light is coming in on this side. So the center of curvature is on the same side of the mirror as the outgoing light, right? Because the light from the object comes here and then it bounces off. And the center of curvature is obviously on the same side of the mirror now as the outgoing light. So we say that the radius of curvature is positive. So R is positive here because it's on the same side as the outgoing light and the same side as the center of curvature. Now, in the case of a convex lens, so for a convex lens, we have the light here, it bounces off, and then obviously goes out in this direction. So now the center of curvature is on the opposite side. So that means that our radius of curvature is negative because the center of curvature is on the opposite side as the outgoing light. So here, R is positive, here, R is negative. Okay, so now let's derive an equation for the relationship between the image distance and object distance for a spherical mirror that is concave. So here we have a object, some point object here at P. We have the center of curvature here. We have the image point here. And then this distance from P prime to from P prime to the mirror is going to be called S prime because that's the image distance. And then the distance from the object to the vertex is S, which is the object distance. So now let's derive, like I said, we're going to derive a relationship between the radius of curvature S and S prime. So, let me add a page here. So the first thing we want to do is we're going to look at this triangle here. So we're going to look at this triangle and this triangle. So let's look at this first yellow triangle. So I'm just going to move this. So for this first triangle, let's just count up. We know that in a triangle there's going to be 180 degrees. So we have alpha, right? Then we're going to have in this triangle, this angle is 2 theta, right? Because this is the angle of incidence here. The normal to the surface at this point goes right here. So we have an angle of incidence theta and then an angle of reflection theta, so this angle is 2 theta. So we have plus 2 theta. And then this angle here, so be careful, this isn't what we're calling phi, it's this angle here. So this angle here, we can write in terms of beta because we know that this here is a flat line, right? This line right here is a flat line. So we know that beta plus this angle has to be equal to 180, right? So if I wanted to just write this angle here, I could write it as 180 minus beta, and that would give me just the measure of this angle here. So I know that that angle is 180 minus beta, and this is all equal to 180 because it's all a triangle, so it's going to add up all to 180. So this I can simplify right away. I can see that this will become alpha plus 2 theta minus beta is equal to 0, right? Because this 180 and this 180 will cancel out. So I get alpha plus 2 theta I can rewrite as beta. So I'm going to keep this equation here for a second. And now I want to look at this little green triangle. So now I want to basically just do the same thing but for this green triangle. So for this green triangle here, this angle now is phi. So I can write phi plus, then this angle here is theta. So phi plus theta is equal to, plus this angle here, which I know again I can just write as 180 minus beta is going to also be equal to 180, right? Because this is a triangle and all triangles have 180 degrees. So I can simplify this now. Phi plus theta is equal to beta. So this just simplifies to this. So let me circle, square that. Okay, so now I want to just get rid of theta. So let's go back to our, here I will just rewrite these equations. We had phi plus theta is equal to beta. And we had alpha plus 2 theta is equal to beta. So I can rewrite this equation as theta is equal to beta minus phi, and then plug that in here to get rid of theta. So alpha plus 2 times beta minus phi is equal to beta. Alpha plus 2 beta minus 2 phi is equal to beta. And then I get alpha plus beta is equal to 2 phi. So now I have this equation here. So now that I have this, I'm going to look back at what I just had before, and I'm going to write the tangent for all of these angles. So I'm going to write tan. So tan of alpha, remember, is opposite over adjacent, but you need a right triangle. So I can use this triangle. So let me erase this. So now I want to look at this triangle, because that's a right triangle, so I can use tangent. So tan alpha is going to be opposite over adjacent. So that's going to be tan alpha is the opposite side here, which is h, over this distance. Now, from P to the vertex here is the object distance s. So this distance is just s minus this little delta here. So this is just the distance from down from this point to the vertex is just delta. And we're going to see delta is going to cancel out anyway, so don't worry about that. So tan alpha is h over s minus delta. Now I'm going to do tan beta. So tan beta, I can do the same thing. Look at this triangle instead. Oops. So now I want to look at this triangle. So this triangle, beta is going to be opposite over adjacent, so it's going to be h over, now here from P prime, this is the image location, so from the image location to the vertex is s prime, that's the image distance, right? So this is s prime minus delta will just give me this adjacent side here. So tan beta is again h over S prime now minus delta. And now I just want to do tan phi. So tan phi, right here, you can guess what triangle I'm going to be looking at. I'm going to be looking at this triangle here. So this triangle, the opposite side is H, and now phi here was the angle that was made from this perpendicular, the line that was perpendicular to where our rays met our mirror. So if you think back to geometry, if you have a line that's meeting a circle at its tangent and it's perpendicular, it passes through the center of the circle. So the distance here, this is just one radius, since it's passing right through the center of curvature. So the opposite side is H, and then the adjacent side, this right here, this whole thing is the radius, so this is R, and then this little side right here is just R minus delta. So we have R minus delta for tan phi. Now we're going to make an approximation. So we're going to say that this, the equation that we're eventually going to derive now is only valid for small angles of alpha. So only if this angle alpha is very, very small. So basically if you have, your object is like very far away from your mirror, or the radius of curvature is very big, that's what this is going to be valid for. So when we have very small angles, we can use a small angle approximation. And remember, the small angle approximation that we did a couple of lectures ago, we said that sine of theta is equal to theta and tan of theta is equal to theta at small angles. So now I can say, since we're looking at only small angles, tan alpha is just equal to alpha. So this is just about equal to alpha. Oops. Alpha. So now I have H over S minus delta is equal to alpha, and then the same thing for all of these. So then I just have beta and phi. So let me just rewrite all of this here. So I have H over S minus delta is equal to alpha. I have H over S prime minus delta is equal to beta. And I have H over R minus delta is equal to phi. So now I want to replace in this equation that I had here, this relationship between the angles, I want to replace this now. So I'm going to plug all of these things in here. So for alpha, I'm going to have H over S minus delta. For beta, I'm going to have H over S prime minus delta. And then I'm going to have 2 phi, which was H over R minus delta. And now, since this is an approximation, we're saying that S prime, and R are all much bigger than this little length delta here. So our radius of curvature, our image point, our object point are all much bigger than delta. So in this equation here, I can just ignore delta and take it out. And now also you can see that I have H in all of my terms, so H will cancel out from all 3 of these terms here. So now, since I'm ignoring delta and H cancels out, my new equation is 1 over S plus 1 over S prime is equal to 2 over R. So this is my equation now. This is my relationship between the image distance, the object distance, and the radius of curvature for a spherical mirror. And now we derive this for a concave mirror, but you can actually derive the same thing for a convex mirror and see that the same relationship still holds. So I think I forgot to make a separate slide for this equation, so I'll put that in the notes when I upload them. This is a very important equation. We're using this a lot, so it should have its own slide, so I'll add that in when I upload the notes. But okay, so this is what we're going to be using whenever we do spherical mirrors. Okay, so let's move on. We're going to use this when we do examples in a few minutes. So now for a concave mirror, we actually get a real image. So before, when we had those plane mirrors, we were just getting virtual images because the light rays weren't actually passing through the image point. But you'll see if you draw your rays for a concave mirror, your rays actually pass through the image point. So you can see here your rays go right through the image point. So this is a real image. You can also say that your light rays converge on the image point, which is why sometimes you'll see also a concave mirror is called a converging mirror. And now this is really important for cameras and telescopes and everything, because if you if you had lab in person, you would actually do this in lab, but we don't, obviously. So let's say if you dim the lights and just had your object here illuminated, it would send out rays, and they would obviously all converge here. And if you put a piece of paper right here at the image point, you would actually see the object. So you would see an image, a real image of the object. So that's why it's called a real image, because there's a real image there. Okay, so that's a real image when you have those rays passing through the image point. So now, as I said before, A, telescopes use this, and B, we were looking at only very small angles of alpha when we did that approximation a minute ago. So what can happen is that your rays, if either your mirror is not adjusted properly or your angle alpha is not small, what will happen is your rays won't converge here. So they'll kind of get spread out, where some of them might go through here, here, here. So the image will be a little bit spread out and it won't converge at a single point. So this is called spherical aberration, and this actually happened with the Hubble. When they first launched the Hubble, they spent however many years doing it. It cost $2 billion. When they launched the Hubble and they took the first pictures, they realized the pictures weren't very good, and that's because I think it was the curvature of the mirror was off by less than a human hair. The curvature was off by, but it was enough to completely mess up their pictures. So this is what one of the pictures looked like with spherical aberration, and that's because the image of this star was not getting focused on on the image point here. So it was getting spread out and you couldn't really see anything very well. So then once they had to send up a crew and correct the Hubble Space Telescope, do a spacewalk and everything, and correct it. And once they corrected it, then they got much better pictures. So we'll see how telescopes work on Thursday, but this is spherical aberration, and it's a very real problem that when you're making telescopes you have to watch out for. So in the case of a telescope, let's say, when the object is very far from the mirror, so essentially your object distance is infinite, especially for a telescope when you're talking about trillions and trillions of miles, that's essentially infinity. The incoming rays are basically parallel. So you can think of that as this point moves further and further away, the rays begin to just look like they're coming in directly parallel with this axis here. So you can see that if you replace the object distance s with infinity, we know 1 over infinity is 0. So then your equation that we found before just simplifies to 1 over s is equal to 2 over r, because this is 0. So then you just get that the image distance is r over 2. So it's just the radius of curvature over 2, and that's going to be where your image is. Now this is called the focal length. So when you have these parallel rays, or basically an infinite object with parallel rays come in, where those rays converge, that image point is called your focal point, and the distance from the vertex is called the focal length. And we denote the focal length as f, and for a spherical mirror, the focal length is just r over 2. So we're going to be using this a lot, especially on Thursday. We're going to be doing a lot of stuff with focal lengths when we do lenses, but this is the focal length. It's just defined by where those parallel rays converge when they are reflected off the mirror. So you can see here, when we have our parallel rays come in, so our object is at infinity, our parallel rays come in, they're all reflected and go through a single point, and that is called the focal point, and it's a distance f away from the vertex, which is the focal length. So here you can see the object distance s prime is equal to r over 2, which is equal to f, the focal length. And here, more sign convention, our focal point, our focal length is positive because the focal point is on the same side as the outgoing rays. So it's the same kind of convention as the radius of curvature, where we look at the outgoing rays. So both the center of curvature and the focal point are on the same side as the outgoing rays. So that means that both R and our focal length are positive. And now the same is true in reverse. So if we take an object and put it at the focal point, the rays from that object will go out, reflect off the mirror, and they will all reflect completely parallel to each other. So this is also, you can also define the focal length this way, where if you put an object at that point, the reflected rays will all be parallel. You can equally well define the focal length that way. So this again is for a concave mirror, so this is what an object at the focal point will look like. Okay, so since we know that the focal length is r over 2, we can rewrite our previous equation just as this, where we just replaced r over 2 with the focal length. Okay, so let's see now for an extended object with a spherical mirror. So again, you can do some more geometry, and you'll see that this triangle here, if you put an object here with some height y, do your reflected rays, and you'll find that this triangle and this triangle are similar, and then you can show that the image height, y prime, divided by the object height is the same as the ratio of the image distance divided by the object distance, but negated. So that we say that the magnification for a spherical mirror is given by negative s prime over s. So the negative is important because remember, in some cases we're going to have s prime will be, it can be positive or negative. So that's important to remember that there's a negative here because that will obviously change our magnification. So in the case of a plane mirror, we had that the lateral magnification was just +1, right? Because you're upright, you look at yourself, you're in the same direction, you're the same size as in real life. So when your image is like upright, we say that that image is erect, and if it's upside down, then we call it inverted. So in our case here, we have an inverted image because it's upside down, essentially. If the magnification is positive, it's upright. If it's negative, then it's just upside down or inverted. So again, we'll see examples of this in a second. So let's do an example. So here we have a concave mirror forms an image on a wall 3 meters in front of the mirror. So we have the image. So S prime is 3 meters of a headlamp filament 10 centimeters in front of the mirror. So the image distance is 3 meters, the object distance is 10 centimeters. We want to know what is the radius of curvature and the focal length of the mirror. So let's find the radius of curvature first. So for part A, we can just write this equation. So we had 1 over S was 10 centimeters. So I'll leave it in centimeters because it's going to be a little bit easier that way. And then S prime, we said was 3 meters, that's 300 centimeters, is equal to 2 over R. So now all we have to do here is solve for R. So now here all you have to do is solve for R and be very careful. I'll put in all the steps in the notes when I upload them, but be very careful when you're adding fractions. A lot of people see like 1 over 10 plus 1 over 3 and just make that 1 over 13. That's obviously not how you add fractions. So just be very, very careful when you're adding these and doing the algebra, that you're very careful with your fractions. So anyway, so if you solve this for R, you will get that the radius of curvature is 19.4 centimeters. So our radius of curvature here is 19.4 centimeters, and that means that the focal length, so the focal length will just be half that. So the focal length is R over 2, so that means our focal length comes out to 9.68 centimeters, which is actually very close to the object distance, right? They said that the object distance was 10 centimeters in front of the mirror, and our focal length is 9.68. So it's almost at the focal length, so the rays will be almost parallel when they get reflected, but not quite. So then for part B, we want to find what is the lateral magnification. So the magnification we say is negative S prime over S. So our image distance was, as we said, 300 centimeters, and S prime was positive here because it was on the same side as the outgoing light. So we still have this negative sign here. So we've got a negative, and then divide that by 10 centimeters. So this comes out to negative 30. So our magnification is negative 30, which means it's inverted, but 30 times as big. So then, what is the lateral magnification? What is the image height if the object height is 5 millimeters? So the actual object we're looking at is 5 millimeters. So we have 5 millimeters, but we know that it's magnified 30 times, right? We said it's 30 times as big. So we just multiply this by 30, and we get 150 millimeters. And then it's inverted, it's upside down. Okay, so that's our first example. So as I said before, I think that this section is hard just because there's so many sign conventions to keep straight, and if you just get one single little sign convention wrong, or you just get confused, like your whole problem will be wrong. So it's very, very important to make sure you know your sign conventions very well. As I said before, be really careful when you're adding up your fractions. But otherwise, I don't want to say it's too hard, because once you just get your sign conventions, the rest of it is like very straightforward. But the sign conventions can be a little bit unintuitive, so that can definitely very easily trip people up. Okay, so now we're going to go on to convex mirrors. So convex mirrors, you can do the same thing with alpha, beta, and phi, and I highly suggest that you do, because going through some of these derivations, that's like really the best way to learn the material. So it's a good idea to do these derivations on your own. The derivation is also in your book if you want to follow it, but you can do the derivation similar to how we did with the concave mirror, and you'll get the same equation basically. You'll get that 1 over s plus 1 over s prime equals 2 over r equation. So for a convex mirror, we have pretty much the same thing, except we have some different signs, right? So we have r is negative now, so the radius of curvature we say is negative because it's on the opposite side as the outgoing light. The outgoing light is obviously here. S is positive because our object is on the same side as the incoming light. But now the image distance, S prime, is negative because our image distance now is here. Because if we have a ray that goes here, bounces off, it looks like the ray is coming from a point on the other side of the mirror. So now our image is on the opposite side as the outgoing light, so that is negative. And we still have the same equation for the magnification. So the magnification is still the image height divided by the object height, which is equal to negative s prime over s. And we said since for a convex mirror, s prime is negative, that means that our magnification will be positive and our image will be upright, because now we're going to have a negative here, and then s prime itself is negative, so our image will always be upright. So you basically have for a concave mirror, your image is always inverted, and then for a convex mirror, your image is upright. And you can kind of even just test this out, like if you get a spoon and you look at yourself on the concave side, you'll be upside down. And if you look at yourself on the convex side, you'll be right side up. So you can test this out yourself if you want. Okay, so now let's talk about the focal point for our convex mirrors. So for a convex mirror, as we said, r, s prime, and the focal point, the focal length are all negative because they're on the opposite side as the incoming light. So we can see here if we have light coming in parallel, so we have our object is very far away. The light comes in essentially parallel, and if we trace back the reflected rays, it looks like they're all coming from a point on the other side of the mirror. So that's our virtual focal point. Okay, so then we just have the same thing, just rewritten here. So this shows both versions where we have incoming parallel rays look like they're actually coming from a focal point back here. And likewise, if you have some light rays that are aimed at the focal point, so if they're coming in here and are aimed at the focal point, they will be reflected parallel. Okay, so let's do another example. So now here we have Santa checks himself for soot using his reflection in a Christmas tree ornament 0.75 meters away. So that means S, our object, is 0.75 meters away. The diameter of the ornament is 7.2 centimeters. So the diameter is 7.2 centimeters. That means the radius is going to be half that, right? So our radius of curvature is 7.2 divided by 2 centimeters. Standard reference text state that he is a right jolly old elf, so we estimate his height to be 1.6 meters. So that means his height, so y, is 1.6 meters. We want to know where and how tall is the image of Santa formed by the ornament. So let's find where he is. So where's the image? That's S prime. So S prime, we're going to use this equation. So let's use centimeters for this. So 1 over 75 centimeters plus 1 over S prime is equal to 2 over 7.2 divided by 2 centimeters. So again, solve for S prime, and you get that S prime is equal to negative 1.76 centimeters. So the negative just comes right out of this equation, so you don't have to worry about whether S prime is positive or negative. When you're thinking about the problem, the equation will it'll just spit out a positive or negative. So we get a negative 1.76 centimeters here. So that means that it looks like Santa is like basically 2 centimeters behind the surface of the ornament. So now we want to know how tall he is. So first, we can use, let me add another page. So first, let's use the magnification we know is this, which is also equal to this. So let's first find, since we know S and S prime now, let's find the magnification. We know his height, and then we can find Y prime. So let's find the magnification is negative 1.76 because S prime we got negative, and then S we said was 75 centimeters. So this is all in centimeters. So M comes out to 0.0234. So this is the magnification. So that means he's significantly smaller because this magnification is much less than 1. So he's significantly smaller than his actual self in the ornament, obviously. So the magnification is positive 0.0234, so that also means that he's going to be upright. And then now we can use this to find y prime. So now we have m is equal to y prime over y. So we can find y prime. I think I said we were looking for y before. So we can find y prime is going to be m times y. So the magnification is 0.0234 times the object height, which we had as 1.6 meters. So now we multiply that out and we get 3.8 centimeters. So the object height, the image height is 3.8 centimeters, and that makes sense because in a little, Christmas bulb, you would expect to have a small image. So so we have how tall the image of Santa is, and we know whether it's erect or inverted. We said since the magnification was positive, that means that it's erect or upright, and that is all we need to do for that. So Okay, so now we're going to just quickly look at the graphical method for finding the focal point and the image height. I don't think that we're actually going to use this that much because usually you use this in lab since we don't really have lab. At least I don't know what 52A is like now that it's online. So I'll do this quickly, even though since we're not in person, we probably won't end up using it very much. But there's, graphical way to find all these things. So basically what you do is you draw 4 rays. So you draw your first ray that's parallel to the optic axis here. So you draw one ray that's parallel here, and then you know how it reflects. The angle of incidence is equal to the angle of reflection. So it will reflect off, and you just draw it, whatever angle that is, you just draw it off here. Then you draw a second line. You draw a ray that goes through the focal point. So then you draw a ray, this here, number 2, that goes right through your focal point. And again, see how it reflects off. Draw your reflected ray. And then, and that's your second ray. Then you're going to draw a ray along the radius. So your ray is going to go along the radius, go right through your center of curvature, and then now since it's hitting the mirror at a perpendicular angle, it's just going to be reflected right back. So it's just going to go straight through that center of curvature there. That's your third ray. And then your fourth ray is going to go to the vertex. So this fourth ray here, this pink one, you're going to draw it straight to the vertex, and then you're going to see how it's reflected. Angle of incidence is equal to angle of reflection, and you're going to draw it back here. And you're going to see that they all meet at the same point. So obviously all 4 of your rays here met right here, and that shows you your image height. So you go from the optic axis here to this point where they all meet, and that's where your image is. So that will give you your image distance, and then this height here where they meet, the distance from the optic axis to where they meet, is your image height. And then you can do the same thing for, this is for a concave lens, a concave mirror. You can do the same thing for a convex lens. But for a convex lens, it's a little bit more complicated because you do, so you start off the same way. You draw a ray that's parallel to the optic axis, it gets reflected off. Then you have to trace it back to see where it looks like that ray originally came from. So then you trace it back, and it's going to look like it's, and so that's going to look like it's going straight through the focal point, right? Because we know if a ray comes in parallel, it looks like it's coming from the focal point. Then for our second ray, we do a ray that goes towards the focal point. So then we have a ray that goes towards the focal point. So it goes from here to the focal point. If it's going towards the focal point, it gets reflected parallel to the axis. So now this angle, this ray is parallel to the axis, and again you extend it back. You extend the reflected ray back here. Then you do the same thing for ray 3. You have it meet the mirror at a perpendicular angle, reflect it back, see where it looks like it's coming from. It's going to go straight through that center of curvature. And then for your fourth ray, you do a fourth ray that's here, meets your vertex, gets reflected off, see where it looks like it's coming from, so trace it back. And again, you're going to see that all of these, they shouldn't really have this green one here. I think that's a little bit confusing, but all of the rays that were reflected when you trace them back, again, all look like they're meeting at this one point. So that will give you your image distance, and then the height of that will give you your image height. So that's how you do it graphically. Like I said, we probably won't need to do that in this class. You might need to do it in 52A, so it's worth knowing. But anyway, okay, so that's the graphical method of figuring out the object distance, the magnification, if it's inverted or upright. So, okay, so now we're going to look at refraction. So, I don't know why, okay. So when we have a plane, in this case a flat plane surface that has 2 different indices of refraction on either side, we're going to have something similar to what we had before happen, where we have an object over here, we draw the rays, they refract out, and if we're on the other side of this interface here, it's going to look like the rays are actually coming from somewhere else. So here, if you just draw the refracted rays back along a straight line, it looks like your image is right here. So now we have an image over here, and so that's what happens when we have, instead of a mirror where the rays are just reflected, now we have our an interface with two different indices of refraction, and our light rays are refracted instead of reflected. So let's see how this changes things. So I'm not going to go through the derivation here. Again, I highly recommend you do it yourself, but we're just going to skip straight to the answer, otherwise we'll go way over for time. So here we have some, now instead of it being flat, we have some radius of curvature here. We have an object here, the rays come into this interface, and then they're refracted, and they all meet again at an image point P. We still have a radius of curvature here. So we're going to have a relationship between the indices of refraction, the image distance, and the object distance. So that is given here. So obviously NA is our first index of refraction, NB is the second. We have our image distance, S prime, and then we have our object distance here, and then we have the radius of curvature here. And again, you have to keep track of whether they're positive or negative. We're going to be using the same sign conventions as before with mirrors, where R is negative if it's on the opposite side as the outgoing rays. So here our radius of curvature is positive now, because you can see the outgoing rays, they hit this interface and then they go out on this side, right? And now our center of curvature is on the same side as the outgoing rays, so R is positive now, whereas previously it was negative when we had the mirrors. So now R is positive for this case. And then in this case also, we just saw that S prime is now positive because it's on the same side as the outgoing rays. And then also our object distance S is still positive because it's on the same side as the incoming rays. So, okay, so now we have this equation that governs refraction. And then we also are going to have a similar equation that governs the magnification now. So again, I'm not going to go through the derivation, but we have now this equation where we just have the index of refraction of the first medium, the index of refraction of the second medium, and we still have that negative S prime over S. Okay, so, all right, so here's the sign rules again. I just went over that, so I'm going to skip this for now. Now, in the case of a plane reflecting surface, things are just a little bit different. So we have this equation that we just had. But in the case of a plane surface, so when we have just like a, like a straight flat mirror, the radius of curvature for a flat mirror is infinity. So here the radius is actually infinity, because if you take a circle that has infinite radius, it will basically look flat when you look at it. So the radius of curvature here is infinity. So if I replace R with infinity, that means that this term here goes to 0, because now I have, NB minus NA, whatever that is, divided by infinity, so that will give me 0. So for a plane refracting surface, I get NA over S plus NB over S prime is actually equal to 0. And now that's my equation that relates the object distance and image distance when I have a plane refracting surface. And again, I forgot to write a special slide for that, but I'll put a slide in when I upload the notes. So now for the lateral magnification, so in the case of the mirror, we had NAS prime over NBS. But now from the equation that we just have here, I can rewrite NA over S as negative NB over S prime, right? So now, so this I just got from right here. And now let me rewrite my magnification a little bit. So I'm just going to rewrite it as NA over S times S prime over NB. So I just rearranged these terms in here so that it looks like this. And now I can see that I can replace NA over S with negative NB over S prime. So if I do that, I will get negative times negative NB over S prime times S prime over NB. And I can see that that's going to end up being just positive 1, right? So for a plane refracting surface, my magnification will always just be +1. So the image will be the same size as the actual object, and it will be upright. And again, I'll put this all on a separate slide that's a little bit clearer since I forgot to make a special slide for it, of curvature 2 centimeters. So that means if you drew out a little circle here, this radius of curvature, the radius would look like it's about 2 centimeters. So a small object is placed on the axis of the rod 8 centimeters to the left of the vertex. So right here we place an object that's 8 centimeters. Find the image distance and lateral magnification. So the image distance first, so we have, let's write everything out. We have R is 2 centimeters. We have the image distance is 8 centimeters. We know NA is the index of the first index of refraction where the object is. So that's 1. And B is the second index of refraction, so it's 1.52. And we want to find first the image distance. So we can use our equation that we just had here. So let's plug in NA, we said is 1. The object distance was 2 centimeters, so everything here is going to be in centimeters, so we don't have to worry about units. NB was 1.52. We're looking for the image distance. NB minus NA is 1.52 minus 1, so we have 0.52. The radius of curvature we said was 2 centimeters. This was 8 centimeters was the object distance. Okay, so now we just have to solve for S prime. So again, you just go through some algebra. I'll put the details on the full notes when I post them. So go through and solve for S prime. And when we do that, we get 11.3 centimeters. So that's positive. So we got a positive there. So that means our image is on the same side as the outgoing rays. So since they go right through the surface here, that's going to be over here. So now we found that. Now we want to find the lateral magnification. So the lateral magnification for part B, we can just use this equation. So remember, we have to have our indices of refraction here. So we have for NA is just 1, NB is 1.52, S is positive 11.3, S prime was 11.3, and then S is 8. This is all in centimeters. So this comes out to negative 0.929. So our magnification is negative, which means it's inverted, so it's upside down from its original position in the image. And it's slightly smaller than the actual object. So now we have the same problem, but we just have a different index of refraction for our first index of refraction, our first medium. Okay, so we want to find the object distance again. We want to find the image distance again and the lateral magnification. So we're going to have the same equation. So let's just write NA we have is 1.33 because it's water, and B is still 1.52. The object distance is still 8 centimeters, and we want to find first the image distance. So we're going to use this same equation. So we have NA now is 1.33 over 8 centimeters plus 1.52 over S prime is equal to 1.52 minus 1.33 over 2 centimeters. So now you do your algebra, solve for S prime, and we get that S prime is now equal to negative 21.3 centimeters. So now a negative pops out of there when we do our algebra to solve for S prime. So that means since we got a negative image distance, that means that our image on the opposite side is the outgoing light. So the outgoing light is over here on this side of the interface. So that means our image is actually over here, 21 centimeters over here. So that's where our image is now. And now we want to find the magnification. So the magnification, we can just use this equation. So we have NA is 1.33 and B is 1.52. S prime is negative 21.3. S is 8. This is all in centimeters. And then that gives us positive 2.33. So now our image is upright since it was positive, and then it was also 2.33 times as big. Okay, so again here, this wasn't too bad. Just the confusing thing is, again, keeping track of all your signs and making sure that you have the correct sign convention. Okay, so now let's do one last example. So here we have, we look straight down into a swimming pool that's 2 meters deep. How deep does it appear to be? So what we're going to do here, so this is our interface. The bottom of the pool, just pretend there's some object at the bottom of the pool, right? So just, draw like an imaginary line PQ, so that's our object. And the object distance now is 2 meters away. So S is 2 meters away. Our image is like, how close does that image on the bottom of the pool look? So that's going to be the image distance is what we're looking for, right? So some imaginary image at the bottom of the pool is how far away. And then our NA, we have to be careful here because you might think that NA is 1 and NB is the index of refraction for water, but that's actually not true because our object that we're looking at is the bottom of the pool, right? So it's this line PQ on the bottom of the pool. So that's where our object is. That's where our light rays are really emanating from. So our NA is actually the index of refraction of water. So NA is actually 1.33. And this is really important because obviously if you don't get your indices of refraction right, your whole problem will, you'll get all wrong negative signs and stuff. So NA is 1.33 and NB is the index of refraction of air. So now we can just use the equation that we had before, NA over S plus NB over S prime is equal to 0, right? Because remember our radius of curvature is infinity when we have a flat surface, so it's just 0 on that right-hand side. So now we can just plug in 1.33. S is 2 meters plus NB is 1 divided by S prime is equal to 0. And now we can just solve for S prime. And for S prime, we get negative 1.5 meters. So S prime is negative 1.5 meters. So that means the image distance is on the opposite side as the outgoing rays. So the outgoing rays are over here. So our image distance is over here, and it's 1.5 meters away from the interface. That means it looks like the pool is actually 1.5 meters deep. Okay, so that's it for today. So I know there's a lot of like sign conventions and negatives and stuff. So Thursday we'll do some more lenses, cameras, telescopes, stuff like that. Okay, so I will see you guys then.